Thank you for having me. Thank you for being here. Let me tell you a little bit very briefly, just to situate you. I work at the University of Arizona. I'm in the chemistry department there. And most of my research is focused on analyzing chemistry reasoning, either student reasoning or expert reasoning in the discipline. And we use that research to develop strategies to foster what we call chemical thinking. That is the idea that there are chemical ways of thinking and acting in the world that are very useful to answer questions and solve problems in different contexts. So what I will be doing in this talk, I guess the goal of my talk today is to give you a sense of the type of investigation that we have been conducting, because I think it's very important for you to understand the type of educational changes that we have been implementing and the challenges that we are facing to implement them at the University of Arizona. So my talk will be mostly divided in talking a little bit about the research that we have done and then presenting the type of changes that we have implemented, mostly in the foundational course that for us is general chemistry. I assume that many of you know that by now research in science education has identified many challenges that we face with traditional teaching in the sciences that have to do with problems with motivation in the students and also the type of learning that they occur. And this is just a small summary of things that people will highlight as problems that we have, from alternative conceptions to low self-efficacy, etc. So what I wanted to present here is because most of my research has been focused on what I would call paying attention to the challenges that the students have in reasoning. Things that have to do with, I will be calling intuitive reasoning, and things that have to do with the heuristic reasoning. So most of the changes that we have implemented in our curriculum are mostly focused on trying to improve those two areas, hoping that that will have an influence on other challenges that we face in science education in general. So what we know is that, at least in chemistry, typically there is a huge difference between the type of reasoning that the students bring to the table when they arrive into our courses and the type of reasoning that we would like them to develop, that we say like more expert-like reasoning. And the challenge is how to do best close the gap between where they come and where we want them to be. And our approach has been to better understand how students reason in the discipline. We also think that, at least in chemistry, there has been very little analysis of how actually chemists think in the discipline. What does it mean to think like a chemist? And that then, once you understand those two, you will be in a better situation to design and evaluate educational environments that actually help close that gap. So my talk is divided in those three things. I'm going to tell you a little bit about what we have learned about the students' thinking in chemistry, very briefly about the studies that we have done to analyze how experts think in the discipline, and then most of my talk will focus on what changes we have been implemented based on that analysis. So again, you can approach the analysis of student reasoning or student thinking in different ways. We have been, in the past 10 years, working with fundamental hypothesis is that many of the challenges that students face in chemistry classrooms have to do with intuitive assumptions that they have about the nature of chemical substances and processes and heuristic decision-making strategies. So when I talk about student reasoning, most of what I'm talking about is about the analysis of what we have done in those two areas. Assumptions that they have and the type of decision-making strategies that they use to decide what is important, what is not important, how to use it to make predictions, build explanations, etc. So let me start with what is that I call assumptions. What is this intuitive assumptions? What is that we call them? In general, I define them as implicit beliefs about objects and events. Every human being has them. I'm going to show you that you have them, so that you understand what is that we are calling intuitive assumptions. I assume that everybody knows that dress, and that different people see it in different colors. So how many of you see it blue, whitish? Okay, so there are people that see them, that would be the streams. So now there are different hypotheses of what this happens, but one of the potential explanations is that the brain makes implicit assumptions about the nature of the light that was used to take the photograph. So if you assume that it was natural light, you will see well, if you implicitly assume, because you are not conscious about that assumption, but if you implicitly assume that it was natural light, you will see it in some way. If you assume that it was artificial light, you will see it in a different way. So you are not aware of that assumption, but that assumption guides the way you interpret the world. Okay? So let me show you a different example. I'm going to give you an experiment to think about, and I'm going to ask you to pair up to discuss your interpretation of the experiment. So that is a representation of a flat surface. You have a ball there represented in a yellow color, and then you have kind of a flat screen that is covering your view. Okay? Just covering your view. And I'm going to show you the experiment. So again, so I'm going to utilize just 1 minute to discuss with someone and come up with an explanation. How would you explain what you see? Okay, so that's enough. That's enough time. So I would like to just to get volunteers to tell me a potential interpretation of what is happening. How would you explain it? Based on the information that you have, what would be your explanation? Please don't be like my students.
So one possibility is that the small ball is heavy and the big one bumped into it and stopped and pushed the other one out.
Okay, so there was another ball behind the screen and there was a collision. So that's one potential interpretation. A different one that maybe you discussed? I heard something about that there. Okay, go ahead.
So we called it perspective change. So as it went through the box, it actually also went what I would call to the left, I guess, or up.
So there is a perspective. It's the same ball, but there we have a perspective. So we have two potential interpretations. You don't really know what is the answer is. No, so I'm going to call those two misconceptions. Because maybe that's not the correct answer. But what I'm going to claim is that independently of what you come up with, there are assumptions that were common in the explanations that you built. So, for example, when I said that this was a ball, I trigger assumptions about how balls behave. Okay? So if I was told you that that was an electron, I would have triggered different assumptions about what that was. And the explanation would have maybe different. So what type of assumptions I'm triggering? Well, for example, I may trigger the idea that, well, if it's a solid object, it will have moving continuous trajectories. So you are not going to come up with an explanation that is, oh, suddenly the small ball appeared, okay, and the big ball disappeared. That would be an unlikely explanation that you would generate because you have assumptions about continuity, coherence in movement in a space, persistence over time. So what I'm calling implicit assumptions are not necessarily the explanations that students are going to bring to the table, but what are the implicit assumptions that are guiding the construction of those explanations based on their beliefs about how electrons or atoms or balls behave. So the claim is that whenever we ask people to build explanations in biology, chemistry, physics, etc., those explanations sometimes do not align with scientific explanations because the assumptions that are made are very different from the assumptions that scientists have uncovered as the better explanations or better assumptions to explain this type of phenomena. So we have done a lot of research of trying to uncover what are those underlying assumptions that guide the student reasoning in chemistry. And over the years, we have identified many of them. And we call them additivity, centralized causality, teleology, etc. That doesn't matter at this moment. I'm just telling you that we have uncovered a set of assumptions that essentially paint a picture that students that come to a chemistry classroom in general think of chemical substances and processes as working with composite objects. They are made of different pieces. Those pieces have inherent properties. You can mix them. You cannot mix them. You have to invert energy. You have to invest energy to mix them. You have to invest energy to demix them. You can hide the stuff inside those things because they are composite objects that could keep things together like energy. You can release that energy if you open those objects. So there are ways of thinking about chemical substances and processes that reveal underlying assumptions about how the world behaves. And unfortunately, those assumptions do not necessarily align with the assumptions that chemists do to explain chemical substances and phenomena. So just to give you an example, imagine that you ask your students, you have two substances, one blue, one yellow, and they undergo a chemical reaction. You have a new product. And you ask them to predict the color of the new product. So we know as chemists that that is a not very productive question, in fact. We cannot make that prediction. We don't have enough information. But that's because we have different assumptions about what color means and how color is generated in substances or where the color comes from. But for a student that has an additivity assumption, this question is easy. Okay? The color should be green, very likely. Well, we have asked that question to students entering general chemistry, finishing organic chemistry, finish bachelor's degree in chemistry, and after 1 year in graduate school, just to get a sense of how things change. And you can see that, well, things improve, but it takes like 6 years to get to 10% of the people selecting the, And who knows, because this is not a longitudinal study. This is not the same people that we have tracked. This is just samples of different people. So it could be that we never changed their minds. It's that we just lost them in the process. Yes, that we. So what I'm saying is these type of assumptions are very difficult to change, and traditional teaching is not helping very much to change them in a student's minds. So that's one issue that we wanted to address. The other issue has to do with how students make decisions, because in chemistry, there are many of the things that we have to resolve depend on making decisions about what factors are relevant to make predictions about what is happening in the world, or what factors are relevant in predicting the properties of substances, etc. So understanding decision-making is pretty important if you want to understand how students think. So we have followed this idea of trying to explore the heuristics or the mental strategies or the shortcuts that the students try to use to generate explanations or to make decisions. And I'm going to show you also that you have the same type of mental strategies. This is not that special that the students have. It's just that it happens. It's human nature to have them. So let me ask you this question. I'm going to show you 2 different types of milk, and I'm going to ask you to choose one. Okay, quickly, without thinking. You just tell me, I want to buy that one. Well, if you're normal, most people select the one on the left. Yes, without knowing actually nothing about it. Yes, so something is triggering a decision-making pattern that is implicit, that leads to in a certain direction. So for example, who would you trust? Yes? So there are decision-making strategies that we use that are called heuristics, very well explored in the social sciences, that allow us to make very quick decisions. They are very useful for survival. And we wanted to explore to what extent where our students were using it to make decisions in their classroom, in the chemistry classroom. So what we did is we have done a set of experiments trying to ask the students questions that involve decisions. So for example, imagine that you want to design a can burner and you have 2 options for your fuel. I give you the options in this way. I could give you the options in different ways. I could tell you the names. I could give you the formulas. That is going to impact actually the outcome of the decision making is. This is not an easy decision. There are many factors that you could consider, but we have asked the question just to explore how students make the decision. And what we have found is that many of them select that. Okay? Now, how do they make the selection? Not at the beginning of the course, but after completing a course in chemistry, is typically goes in this way. They focus on what is the most salient differentiating characteristic. And in this case, the most salient differentiated characteristic is that one has an O and the other one doesn't have an O. Then they tend, if possible, and that's when assumptions come in, they tend to associate, based on implicit assumptions, how that feature could help to make that decision. So for example, in this case, there is an O. They likely know that O means oxygen. Oxygen somehow is associated with combustion. Oxygen somehow helps combustion. So, well, let's go with that one, because it has oxygen in it. So now that reveals also what we call an additivity assumption, no? That to think that chemical substances are just like a combination of carbon, hydrogen, and oxygen, and the properties of those things survive, no? the chemical process of forming that substance. And then they unconsciously substitute one difficult question by a simpler one. So instead of saying what is the better fuel, they are answering the question which one has oxygen in it. So we have done this type of research with different students, different type of levels, and we have seen that most of our, at least my students at the University of Arizona, and I understand that the population of my students is very different to the population of your students, but many of my students survive chemistry courses by being very good at applying recognition, similarity, and one-reason decision-making to select what is the answers that they have to answer with. They don't use chemical ideas, they just use these heuristics to identify the best answer when they are presented with different options. So that's a different challenge, but those are the two main challenges that we wanted to try to address. How do we transform the assumptions that the students bring to the table when trying to deal with a chemical question, and what type of heuristics they use to make decisions? Now, I don't think this is only a chemistry issue. No, there are studies in biology, studies in physics, for example, that show that underlying assumptions and heuristic decision-making has a lot of impact on how students make build explanations or make predictions in the classroom. So that is one side of the story. The other side of the story is analyzing better how chemists think, just to get a sense of how far, what is the distance between where students are and where we want them to be. So like in many sciences, no, chemists rely a lot on mechanistic reasoning, and mechanistic reasoning in our interpretation is essentially you identify a target system that has certain properties and behaviors. You build a model system that has certain components that have certain properties, typically have interactions between them. And then you build causal connections between your model system and your target system. Now, in chemistry, when you compare the assumptions that experts made to the assumptions that students make, you can see a huge difference between thinking of substances as composite objects that have pieces that you can separate, to thinking of substances actually as processes. So you have a lot of stuff there interacting with each other with emergent properties, in which there is a lot of variability, a lot of randomness that is biased by the structure of the things that are happening there. So there is a huge difference between the assumptions that students bring to the table and the type of assumptions that we want them to use to make productive application of chemical thinking. So a lot of our research has been centered on identifying where the students are and where experts are expected to be. The other thing to recognize, and again, this is not a case only for chemistry, it's a problem of all sciences, is that in general, when we talk about the type of predictions and explanations that we want our students to make, those explanations and predictions require to think in multiple scales, using multiple types of representations, looking at multiple variables at the same time, looking at implicit cues, that is very difficult for a novice and then making multiple decisions. If you think about what we call the change between composition to properties in chemistry, there are a lot of decision-making points that have to be made that imply looking at many implicit cues that students are unable to do with the type of decision-making strategies that they apply. So those are the problems. We have a huge gap between where students are and where we want them to be, and where we want them to be is actually complex. When we think about the type of thinking that we want them to develop, it's actually complex thinking what we want them to be able to do. So what is that we have been doing, at least at the University of Arizona, to close that gap, and mostly working with the students in the foundational course that is general chemistry. I'm going to simplify things in education, but in general, when we talk about change in education, many people think about modifying instruction. That would be my assessment of many of the changes that have been implemented across the US. And there are fewer changes that are focused on, first, let's rethink curriculum and see how that rethinking curriculum is going to impact the instruction that we want to have. So our approach to change has been starting there. That doesn't mean that we are not going to modify instruction, but we decided that we wanted to rethink the curriculum first, and that the rethinking of the curriculum was going to drive the type of instruction that we were going to have in the classroom. So most of our, let's say most of our intellectual effort has been focused on rethinking the Gen Chem curriculum. Now, we started by recognizing issues that many people have recognized, not only in chemistry, but in many of the science courses at the foundational level. There is an imbalance between extension and depth, between segmentation of ideas and integration of core understandings, our emphasis on learning knowledge versus developing ways of reasoning, the algorithmic versus the conceptual divide, and then our emphasis on thinking about traditional problems versus problems that are relevant to the population of students that we work in. So we recognize those issues, and we focus most of our attention on how to transform the curriculum to change the emphasis from having students learn what we know to try to help them develop the type of thinking that we have. So what we did is first to have a metaphor shift. Let me call you that, try to call it that way. In chemistry, and again, I will say that this applies to many sciences, the typical metaphor for the curriculum is a ladder. No, that is, you start learning about atoms, then you learn about molecules, then when you learn about molecules, you can learn about the interactions between molecules, and then you can learn about reactions. So that's the kind of the typical progression of learning. And so we said, can we transform that metaphor to something that looks more like a thinking spider web? That is, can we focus or identify essential questions in the discipline? For example, in chemistry, an essential question is what the heck do I have in my hands? No? How do I analyze what I have in my hands? And then think of what type of intellectual tools and what type of practical tools are needed to answer that question in different relevant concepts, context. So what we did is to identify, we started by thinking, okay, what are those essential questions for the discipline? And said, instead of organizing the curriculum in traditional topics in the discipline, for chemistry that means stoichiometry, thermodynamics, chemical equilibrium, you can almost predict in what chapter in the general chemistry book those things are going to be. So what if instead of thinking that way, we focus the curriculum on what we call core disciplinary practices? That means, how do we analyze substances? How do we make predictions about the properties of substances? How we do control chemical reactions, etc. So we identify what we call 8 fundamental disciplinary practices that we think that are applied across chemistry to solve relevant questions in the curriculum, in real life. And we develop our own resources. So we created a curriculum that has 8 units. Those 8 units are covered in 1 year, 2 semesters. And as you can see, each unit is driven by a general, what we call an essential question. How do we control processes? How do we predict properties, etc.? So we reorganize the content in that way. In the reorganization, we make decisions also about things that we are not essential necessarily to solve to answer those questions as we wanted. And we brought to the table this idea of learning progressions. So we said, if we are going to work in this way, we have to be very careful about how we are going to help students develop these chemical ways of thinking. So this is just to show you an example. This is the first unit of the semester. The progression that we follow is first focusing on macroscopic models to think about answering the question of what do I have in my hands? How do I analyze something? Then we always ask the students to use those ideas to analyze real systems. No? For example, in this case, you can use macroscopic models to analyze the atmosphere of planets. So you have phase behavior that you can use to identify what type of substance you may have there or how they may behave. Then we said, OK, in order to explain this macroscopic behavior, you can use a very simple corpuscular model, not a chemical model, but a physical model working at the submicroscopic level. That model allows you to do more, no? to start to explain the essentially physical changes in our world. Then we make that model a little bit more chemical by talking about the structure of these particles, no? Just in a very simple way, just identifying those, they have composition and structures that are different. That allows you to solve other type of problems. I wanted to present this because we always go back to the context. The contexts are very different, with which we try to show to the students that the different models that we generate are useful to solve different type of questions. And finally, in this unit, we end at the atomic level, where that allows you to answer other type of questions if you are able to know what are the compositions of substance. So we have very carefully thought about the progression of ideas that we present to the students, and to show that those different ideas are not disposable. It's just different ways of thinking about the world that have different affordances in terms of what you can do with them. We have also transformed our assessment. No? Our assessment, these are examples of 8 exams, 8-unit exams. All of our exams are now contextualized. All of them are focused on one essential question, but for example, this comes from Unit 1. It's about anesthetics, but it's about how can you identify anesthetics, or how can you differentiate them based on the ideas that you have. So the exam is contextualized, but the underlying question is always the same for a given unit. In terms of how we work in the classroom, we realized if we wanted our students to understand different types of models, we had to work in such a way that we always had an anchoring problem to solve, and then opportunities for them to explore ideas, develop models, apply those ideas, revise those ideas, and apply them to a new context. So the learning cycle is very, very well known in science education, so it's kind of the basic model that we use to work in the classroom. Typically, we have a central problem that drives our discussions with the students and our work with the students. For example, design a strategy to resolve this problem. We present data to the students, or they generate data, depending of, we can generate data using simulations, for example, in the classroom. Then we work into a modeling piece. They work in making predictions, they revise their models, and then they argue to solve the. So this is kind of a model-based, argument-based kind of environment in which we work. We have developed a variety of resources that are computational resources that allow students to work with these different models at different levels. And we work with them in very large settings. As you can see, we do our best with the constraints that we have to work with. No, we have about around 250 students. We ask students to bring their laptops. They work in pairs. They work with these simulations where they allow them to collect data or to work or to apply the models. So that's a challenge, but as we are managing this with a learning assistance program that allows us to implement it in a better way in the classroom. We are also exploring working in these collaborative learning spaces. Arizona doesn't have a lot of money, so we don't have the money to build a building with these spaces. But what we are doing is adapting spaces in libraries or wherever we find them to be able to transform the traditional lecture hall in spaces that facilitate this work with the students in collaborative groups. Now, just briefly, I would like to tell you about our story, how this happened. We started the change in 2007 with support of the NSF, CCLI grant at that moment. We started just piloting in one section of general chemistry. That means 250 students. We collected data for 3 years. The data was collected in form, we use an ACS, a standardized general chemistry exam. We developed what we call an intuitive chemistry inventory questionnaire. that was focused on what we wanted to measure, if it was changing. And then we also followed the students to see how they were performing in what for most of them is the next course. We collected enough data for the faculty to allow us to extend the project to 2 pilot sections. Then we collected more data for 4 more years. Until in 2014, we were able to convince the faculty that this could be applied to all of the sections of general chemistry. So in 2014, faculty say, OK, you can do it, but you have 3 years, a 3-year trial period. That is ending right now. So it's going to continue. I can tell you that now. No, it's going to continue. We have shown enough data to show that there is positive outcomes. But there are also political issues that have happened in between. No, we were selected as one of the sites for the American Association of Universities. The project was recognized in the NRC project. And that has brought some visibility to the project that has made it more palatable for the entire faculty in chemistry in our department. Just to show you that we have positive outcomes. This is a comparison of with historical data, ACS standardized test, just to show you that if the bar is above the 0, means that our students in the new curriculum are doing better than they were doing before. So in most questions, they are doing better. This is for our IC questionnaire, the conceptual questionnaire. The blue dots are the performance in the new curriculum. This is divided by how they are performing in the ACS, so that you can see that there's improvement in all bands from students that are getting Ds to students that are getting As in the curriculum. These are grades in organic chemistry. In the past 3 years, we have seen improvement or increase in the number of students getting A's and decrease in the number of students getting D's and E's in organic chemistry. All these changes are significant, but they have become, since we moved to the full implementation, they have become small in their size effect. No, they were bigger when we were doing it in the pilot, and they have become smaller once this has become implemented across all sections. Now, that's a huge challenge that we are facing right now, because the reality is that when you have to work with over 300 students every year, you have to work with very different instructors every year. We have a lot of, we have 4 core instructors that have been working with us from the very beginning, but we also have every year 2 to 4 transient instructors that get into the rotation for teaching the class. Although we use common textbook, we have agreed on common core activities in the classroom. We have agreed on common exams, common homeworks. So there is a lot of commonality on what is done in the classroom. Every instructor participates in a 2-hour weekly meeting. Everybody has participated in faculty learning communities where they talk about teaching evidence-based practices. But we have started doing observations in the classroom of all these instructors. And what we have seen is that there is a huge variation on how activities are being implemented. The same activity is implemented in many different ways. Just to give you a glimpse, these are 3 different instructors. This is a look at the interaction patterns that they have with the students after the students have finished an activity and they are discussing with the group. So you can see instructors that spend a lot of time promoting argument. That would be multiple students, multiple interactions. An instructor that spend a lot of time just on a single interaction with a single student. So there is a lot of variation on how they interact with the students. And there is variation, although not as big, on the purposes or the perceived goal of that interaction. Whether that interaction is just a clarifying interaction, if they are trying to build connections, building links to prior concepts, if they are trying to build a larger frame to think about problems. So as you can see, there is a huge challenge once you try to implement that in a large scale, because instructors, although all of them are explicitly telling you that they are agreeing what you're doing or what we are doing, they have very different visions of how you implement this in the best way in the classroom. So just to finalize, I just want to summarize that our change model is based on the idea that if you want to change anything in educational practices, you need to better understand reasoning, both from experts and novices. These are the people that have been involved in either the research. These are the graduate students that over the years have completed the research. And this is the chemical thinking team, instructors that are regularly involved in implementing and transforming what we are doing in the classroom. I acknowledge the support from NSF and the AAU. And finally, thanks to you. And if you have any questions, I will be happy to address them right now. But if you have questions that are more difficult to answer, you can always email me. Okay, thank you.
Thanks so much for your talk. It's really great to hear and see all the things you've been doing. I had a question about the FLC affected learning community and chemistry teaching. If you could say some things about what that looked like, and particularly on the sort of what kinds of things the participants did, and also to what degree was pedagogical development or comfort with different sets of particularly interactional skills part of that.
Yeah, so the faculty learning communities in which most of our faculty have participated were organized centrally by the central administration as part of this AAU project. They were a group of faculty interested in learning about evidence teaching practices. In most cases, it has been focused on reading. No? So for example, this book that is now Make It Stick. So that's, for example, is used as the discussion for, not weekly discussion, the discussions are maybe every other week. They meet for 1 hour. And then they may have a project, no? Kind of a change project, a very small change project that they have to implement in their own classrooms. They get observed by peers, and then that's essentially the dynamics of the FLC. I don't think that there is a lot of time for them to go in depth about discussions about how to actually implement things in the classroom. It's more like an overall view of things that you can do to more actively engage students. Yeah.
I wanted to ask you how you or others arrived at the core disciplinary practices that you ended up forming all the units around, and how much that differed from a list of, say, knowledge versus skills that people would have come up with for what they're trying to teach the students. Sort of how different are they from a skill set?
Well, I wouldn't call them a skill set, because what I call a core disciplinary practice is not just a skill, it's the integration of the knowledge or the core understanding ideas and the practices that are applied to solve that problem. So when I said that, just let me go back.
I wanted to see those again.
Yeah.
How much agreement could you get across faculty developing what these are for their discipline?
So when I said that analyzing substances is a core disciplinary practice, well, what we did is we analyzed whatever resources we had available. There is, for example, a very well-known NRC report in chemistry in 2003 that they were talking about what were the chemistry in the 21st century. What chemists will be doing there. So you can see there is a lot of work on, well, they will be analyzing substances in different contexts. So I don't think that any faculty is going to deny in chemistry that they engage into analytical reasoning to identify what substances you have in that. Now, it's not just the practice. It's not that I just need to know how to do chromatography. It's that how I need to think, what models are used to explain, how those models are used actually to differentiate between substances. So is the integration, or at least we see it as the integration of knowledge with the practice. But I wouldn't call it the practice, the general scientific practice of, oh, I'm doing an experiment, oh, I'm analyzing data. No, it's the practice of how do I go about analyzing a substance? Yeah. What do I need to think about, and what tools I have at my hand to answer that type of question?
Just a follow-up to that, did you find resistance from students that you were teaching process, essentially, rather than facts that they like to hold on to?
Well, there is resistance from the students in different ways. I would say that the most resistance comes from the curriculum does not look like high school chemistry. No? And then, so the resistance comes from, I don't recognize what you're telling me to think about. So we don't start with balancing chemical equations, and most students from high school come with the idea that chemistry is about balancing chemical equations or doing stoichiometric problems. So the resistance comes from looking at something that doesn't look familiar, more than I don't think they are sophisticated enough to distinguish between what I would call practice and integrating an underlying big idea.
Those comments right there could segue into this question, and that is, what have you gathered from the students' feedback that have participated in these courses after these changes, the course evaluation feedbacks? What are you seeing?
Is the question more at the attitudinal level, in their beliefs and things about?
Yes, anything they've expressed.
Yeah. So I didn't show. We have some data that we also compare with historical data about attitudes towards chemistry, and that has also improved. The most significant change has been on recognition that chemistry can be useful to their whatever they are interested in. So there is a big change on recognition. We've put so much emphasis in contextual applications that I think that was expected. They can see a better connection between what they are doing and potential applications in chemistry. Now, the attitude, in general, there is a positive change, but they recognize that this seems to be more challenging than a traditional chemistry course. So we have feedback that has to do with that maybe this is too much work. There is too much thinking involved. There is too much what they perceive as conceptual, because we are emphasizing a lot of conceptual thinking and understanding. That doesn't mean that we are not doing problem-solving mathematical issues. It's just that the conceptual has gained. In this balance, there is more conceptual, not more than algorithmic, but more than it was before. So we have a perception that the curriculum is maybe more challenging than it was in the past. But they don't know what it was in the past. No, it's just that perception is there.
So you talked about curriculum as being the place where you're focusing your attention. So have you taken these principles and applied them to courses upstream in the curriculum or downstream?
I wish. We have tried, well, in chemistry, maybe this is very different in other areas, but in chemistry, there are silos. There are silos in teaching. No, there is Gen Chem, OChem, PChem, AChem, and there is no necessarily interaction because an OChem, someone that is a PChem is not going to teach an OChem course. No, that is not going to happen. So these silos are a challenge because each of those silos have historical ways of thinking about their curriculum. No? So we have tried to work with organic chemists. We have not been successful with organic chemists in Arizona, but now we are working with organic chemists in UC Davis that seem to be more open to think in these ways. So we have been trying, but the discipline doesn't necessarily help.
I think your discipline is not alone.
When you look at student reasoning and problem solving in chemistry, can you trace that back to specific curricula that they experienced in high school or middle school, just in terms of the ways of thinking? Like, for example, anthropomorphizing chemicals.
Let me try to explain my position on that issue. Of course, you can trace many things to the history of each individual. No? I mean, what we explain, how we explain, what we pay attention to depends on what we experienced before and what we have heard before. No? But what our claim is independently of that, there are underlying assumptions that are common to everybody. So what you are going to see is a different manifestation of how those assumptions are applied. But not a difference necessarily on the underlying assumptions that are there. So yeah, we can trace specific manifestations to ways of talking in the curriculum. No? So for example, we know it. If you're a chemist, you know that you love the octet rule. That is a rule that allows you to make predictions about the stability of substances, let's say. But chemists talk about the octet rule in a very teleological way. Atoms love to get 8 electrons. They are more stable when they are electrons. They are happy when they have 8 electrons. That's a way of talking in the discipline that is teleological. Biologists, forget about that. No, they are over the top in that sense. But chemists also have this, have this niche of talking. Now, for a chemist, that's a way of talking, yes? But for a student, it's also a way of talking. I'm not going to say that the students believe that atoms love 8 electrons, but becomes an ending point. No? It's satisfactory enough to know that atoms want to get 8 electrons. Why? Because they want to. Because they are more stable that way. So it becomes an ending. But the underlying assumption is that humans think about the world in teleological ways. We assign purpose to things. No? So what I'm claiming is that independently of their history, there are ways of thinking that are more human driven.
I'm curious about the finding that different professors were doing different things in their classrooms. And did that have to do with their conceptions of teaching, their comfort with active learning methods, their buy-in to the process? If they were, in other words, did the people that were coming and going tend to buy in less than the people that made the program? And the second piece of that is, do you think any kind of pedagogical interventions might help with that?
I don't think I have the answers because we have just started to look at the differences. But I think it's going to be all of the above. No? Is that there are many factors in play. So for example, you would have imagined, that was my hypothesis or not, that the most experienced instructor with the curriculum, the person that was the most involved in the development of this curriculum, sorry about this, would look more like that or not, promoting multiple interactions. No, that person is this person, okay? Why? Because this person goes after students. These single student interactions are in-depth interactions with a single student to try to push, probe, back, forth. Yes? These multiple interactions are, yes, they are great. They are interacting with all the students in the class. Well, not all, but many students in the class. But they are superficial interactions with every student in the classrooms. No? So it's very challenging, even with this data, to know what is going to have the positive effect that you want. No? So this is the most novice of the instructors. This is the most experienced of the instructors. Yeah, in general, the most experienced have the better outcomes. Because it's not only the way they engage the students, it's what they talk about, how they frame the discussions, what they emphasize in those discussions. So the problem with the problems that we are having with instructors is that it's not only a question of knowing how to manage and interact, is the intellectual frame that you bring into the class when you have those interactions. And that's the huge challenge for us. How do we change the framing that the instructor brings to the classroom, not only in terms of how you interact with the students and the value of interaction, it's how you think about your discipline. What is important? What links do you emphasize? How do you emphasize those links? How do you bring students to the table? What do you discuss with them? So the challenge is huge. No, it's just sometimes overwhelming, but
Can I just ask a quick question about the 2 hours a week that you meet as a team?
Yeah.
What do you typically do in that time? What do you think are some of the most important things that you do when you gather together?
Well, the setup is we go over the materials that are going to be covered the following week. We talk about not necessarily the content, but the core activities. We have core activities that everybody is expected to engage the students with. We talk about those activities. We talk about our experiences working with those activities, what challenges we have faced in the past, what type of problems the students not typically have with those activities. So that's part of the discussion. Other part is that we have common exams. So part of that, our discussion is what is going to be the questions that we are going to be posing in those exams. So 2 hours is not enough, no? The reality is 2 hours is not enough, but it's mostly focused on the content in the assessment of the course.
All right, well, I think we're out of time, so we're going to stop there. And thank you once again.